Okay, so hello everyone. My name is Aryan Kumar. I'm 12 years old. I was born in Bihar, but I'm living in Ludhiana for my education purpose. And for today, our topic would be about electromagnetism. Okay, so introduction to elect. Okay, so introduction to electromagnetic synthesis. So it refers to the study and application of techniques that use electromagnetic principles to design or create objects and systems, often in specialized engineering fields like microwave engineering, optics, and material science. So it is a very highly specialized topic that extends beyond the general field of electromagnetism. So Maxwell's equation, the foundation. So Maxwell equation unified electricity, magnetism, and optics into an comprehensive framework. They describe how electric and magnetic fields propagate and interact with matter. So these equations led the groundwork for all modern electromagnetic theories and applications. So while electromagnetism typically involves analyzing existing fields and their interactions that are described by the Maxwell's equations, electromagnetic synthesis is more focused on the reverse processes. So like it is about determining the sources, materials or structures that are needed to achieve the certain electromagnetic outcomes or field patterns. So this foundation refers to the four partial, there are four equations uh, that form the foundation of the electromagnetism. So these equations describe how electric and magnetic fields are generated and interact with each other. So it unifies the previously separate theories into one. So okay. Okay, so I think some new people have joined. Ekamjot has also joined. So thank you for joining us, everyone. So hello Ekam, are you here? Hello Ekamjot. Okay, so Saksham, can you read this slide?
Okay, Aryan. Maxwell's equations light as a electromagnetic wave. Maxwell created a set of four rules for how electricity and magnetism interact. When he solved these rules, they showed that these forces could travel together in a self sustaining wave through an empty space like ripples in a pond. The rules even calculated exactly how fast these waves should move.
Okay, so Maxwell created a set of four rules for how electricity and magnetism should interact. When he solved these rules, they showed that these forces could travel together in a self-sustaining wave through empty spaces like ripples in a pond. The rules even calculated exactly how fast these waves should move. So when these four equations were solved, it came out that light is an electromagnetic wave, and then after solving it we calculated how fast the waves are moving to. Gauss law for electricity. Electric charges produce electric fields. Field lines originate on positive charges and terminate on negative charges. Simply means that electric charges create electric fields, and we can measure by how much charge is inside a space by measuring the total electric fields coming out of it. So we can imagine that it has a putting a box around some charges. If more field lines come out of the box then go in, there's a net positive charge inside. If there are more in than come out, there's a net negative charge inside. So Saksham, did you understand this slide?
No, Aryan.
Okay, so it says that electric charges produces electric fields, and we can imagine it has a box which has, let's say, two holes, and there is one in hole and there is one out hole. So the in hole is positive and the out one is negative. If there are more in that box, the net uh, charge would be positive, and if there are more out, there would be a negative charge inside it. Okay, so did you understand this? Okay. Hello, Saksham, did you understand it?
Yes, Aryan.
Okay, so can you explain it in some simple terms? Hello, Saksham. Hello, Saksham, are you here? Okay, so Gauss law for magnetism. So, Saksham, can you read this slide? Okay, so there are no magnetic monopoles. So, hello, Saksham, are you here? Your voice is not coming.
Yes, Aryan.
So, can you read this slide?
Okay, Aryan. Gauss law for magnetism. There are no magnetic monopoles. Magnetic field lines are continuous loops, always having a north and a south pole paired together. Unlike electric field lines, magnetic field lines always form continuous closed loops. They never start or end at a single point.
Okay, so Gauss's law for magnetism, there are no magnetic monopoles. Magnetic field lines are continuous loops. They are always having a north and south pole paired together. Unlike electric fields, which start on positive charges and end on negative ones, magnetic field lines always form continuous and closed loops. So they never start or end at a single point. So we can imagine the magnetic field loops has a whirlpool. So if we divide the whirlpool, there would be still no positive or negative end, which where they start and end on. So they are continuous and closed loops. So magnetic field lines, they always form with two poles, which is north and south pole. So Sakshim, did you understand this topic?
Mm, yes, Aryan.
Okay, so can you explain it in some simple terms or in your words? Okay, so see that the Gauss law of magnetism is that magnetic field always form continuous loops, and they are closed, so they originate from a north pole and end at a south pole, but critically they continue inside the magnet from the south back to the north. So this means that for any closed surface we may draw we may draw in a magnetic field, every field line that enters the volume must eventually exit it. So it also says that the resulting would be a net count of zero field lines passing through the surface. So there are equal numbers of positive charges and an equal number of negative ones too. Okay, so Faraday's law of induction. So Saksham, can you read this slide?
Okay, Aryan. Faraday law of induction. It describes how a changing magnetic field creates an electric field. You can only generate an electric current if the magnetic field is changing. The faster the magnetic field changes, the larger the electric field or induct, induced current will be.
So, Faraday's law of induction describes how a changing magnetic field creates an electric field. We can only generate an electric field if the magnetic field is changing. So, moving the magnet relative to a wire or changing the strength of the wire itself. The faster the magnetic field changes, the larger the electric field and induced current will be. So, this Farad. So, this says that if we bring an magnet close to an wire, what will happen that uh, they will have their own magnetic field which will try to push back against our original movement. So this is also one of the reason why it takes so much efforts to run a generator. So this was also used for making the first motors. So, Faraday's law of induction in simple terms is this, that we can make electricity by moving a magnet near a wire. So this changes and creates a force on the tiny free electrons inside the wire. So this force pushes the electrons to move in one direction, which will create an electric current and which will give us a very good measurable voltage. And the electricity that we have just created has its own magnetic field that will try to push back against the original flow and the movement, which this is the Faraday's law of induction, and it was used to make the very first motors. Okay, Saksham, do you have any questions? Hello, Saksham.
No, Aryan.
Okay. So someone named as Naveen Singh has joined. So thank you for joining us. And if you have any questions, you can raise in hand and ask us. So Saksham, I have a question for you.
Yes, Aryan.
So if we move a magnet relative to a wire, do you know what would happen?
Can you repeat your question, Aryan? Because there is a lot of noise here.
So if we move a magnet relative to a wire, do you know what would happen?
I think, Aryan,
Yes.
it might introduce an electric current in the wire through a process of electromagnetic induction.
Okay. So can you explain it further? What happens in the wire? Do you know? Any guesses, Saksham?
Aryan, I think moving a magnet related to a wire or moving a wire related to a magnet results in electromagnetic induction and phenomenon that produces an electric current in the wire. This is the foundational principle behind electric generators.
Okay, uh, when we moved the magnet, it created electricity. But how did that happen? What happened in that wire? Do you know?
No, Aryan.
Okay, so that we can make electricity by moving a magnet near a wire, because this changes creates a force on the tiny free electrons that were inside the wire. So this force pushes the electrons to move in one direction, which will create an electric field and its and it will also give us an voltage. The electricity we have just created also has its own magnetic field that tries to push back against the our original movement inside the wire. So this creates some resistance, and this is why it takes so much effort to run a generator. So it is because of these tiny free electrons that were in there in the wire, which felt the force of the near magnet, and which created an electric current and and its own magnetic field, which was against the original movement of the free electrons. So which creates some resistance. So did you get it? Hello, Saksham.
Yes, Aryan.
Okay. Ampere's Maxwell law. So Saksham, can you read this slide?
Okay, Aryan. Ampere Maxwell law. Magnetic fields are generated by electric currents and curiously by changing electric fields. The traditional Ampere's law part a flow of electric charge creates a magnetic field circulating around it. This was Maxwell's crucial addition. A magnetic field is also created by an electric field that is changing over time. This displacement current is essential for electromagnetic waves to propagate through empty spaces where no physical world exists.
Okay, so Ampere's Maxwell law. So magnetic fields are generated by electric currents and crucially by changing electric fields. So Maxwell's displacement current correction. So this was a Maxwell's crucial addition. A magnetic field is also created by an electric field that is changing over time. This displacement current is essential for the electromagnetic waves like light to propagate through empty space where no physical wires exist. By combining these equations, Maxwell predicted the existence of self-sustaining electromagnetic waves that travel at the speed of light, proving that light itself is a form of electromagnetic radiation. So, what this says is that uh, our light is an electromagnetic. Is an electromagnetic wave, and it travels through the empty space at the speed of light. And it also says that a magnetic field is also created by an electric field that is changing over time. So, Saksham, did you understand this slide? Hello, Saksham.
No, Aryan.
Okay, so this says that light is an electromagnetic wave, and it travels through space uh, at the speed of light. It also says that a magnetic field is also created by an electric field that is changing over time. So, okay, so I have one question for you, Saksham. So, do you know why does the Earth have a magnetic field?
Yes, Aryan.
Do you know why the Earth has a magnetic field?
Due to the mantle of the earth.
Okay, so what happens in the mantle? Do you know? Okay, hello, Saksham.
Aryan, there is a lot of voice in my area, so I cannot explain it right now.
Okay, so this happens due to the movement of molten iron in the core. Okay, so wave equation. So it is a linear second order partial differential equation. So that describes the propagation of varieties of waves such as sound waves, light waves, and water waves. So it is a simple mathematical formula that describes how any type of wave moves. It predicts that the wave will travel at a specific speed when applied to electricity and magnetism. So the equation proved that electric and magnetic fields could ripple through waves together as a self-sustaining wave. So a wave equation, so such as sound waves and light waves and water waves, it is a simple mathematical formula that describes how any type of wave moves. So it predicts that the wave will travel at a specific speed. It relates how quickly the wave changes its shape in space to how quickly it changes its shape in time. So so it describes how this electric and magnetic field could ripple through space together as the self-sustaining wave. Uh, Okay. So, Saksham, did you understand this topic?
No, Aryan.
Okay. So this predicts that a wave equation predicts that the wave will travel at a specific speed. So it relates how quickly it is changing its shape in space and how it is changing its shape in time. And so it is used to describe how this electric and magnetic fields could travel through space together as a self-sustaining wave. So did you get it? It describes how electric and magnetic field are moving together. Saksham, did you get it? Okay, so Saksham, do you know? I have a question for you. Do you know what is a flux?
Yes, Aryan.
Do you know what is a flux?
Aryan, I think a flux is a state of continuous change or flow. But in science and technology, it might refer to a rate of flow of substance energy through a surface or a substance that promotes fusion.
Okay, so like I'm talking about flux in the electromagnetism. The flux in electromagnetism. Do you know about it? Yes, Saksham. Any guess?
Aryan, I think it measures the total magnetic field passing through a given surface area.
Okay, so yes, so a flux is a measure of the amount of physical quantity or field lines passing through a given surface. So, in the context of Maxwell's equation, it specifically refers to electric and magnetic flux. So, like we can imagine, it has a flow of water through a net, and the total flux is the total volume of water passing through the loops of the net per unit of time. So, I think so. It is also used in Gauss law of magnetism. So, it is the measure but it is the measure of the volume of water passing through the loops of the net per unit of time. So in a y it can be like how many electrons are passing through the loops of the net or a specific area in an unit of time. So okay, Saksham, do you have any questions?
No, Aryan.
Okay, so okay, Saksham, do you know about Gauss law of magnetism? Hello, Saksham. Saksham, are you here?
Yes, Aryan.
So, do you know about Gauss's law of magnetism?
Aryan, it states that the total magnetic flux through any closed surface is always zero.
So, what does that mean? Do you know?
Aryan, it means that it It is the fundamental principle of electromagnetism. One of Maxwell's equations is expressed as B dot dA is equal to 0, signifying that any magnetic field line entering closed surface must also exit it.
Okay, so can you give an example?
No, Aryan.
Okay, so for this, like we can imagine a box. We can imagine a box, and there are two holes in it. There are two types of holes in it. There is a in one and there is a out one. So in one it enters and it's a positive, and the out one it's a negative. And if the number of in holes are larger, the net charge would be positive. And so what it says is that the number of these holes would be equal, which means the net charge would be zero. So did you get it, Saksham? Okay. Okay, so let's get to quantum electrodynamics. So, a quantum electrodynamics, it is the quantum theory describing the interaction between light and matter through electromagnetic forces. It combines quantum mechanics with special relativity to explain electromagnetic phenomena at the atomic scale. So, it is fundamental in understanding the behavior of photons, electrons, and their interactions. So, basic principles of quantum electrodynamics. So, Saksham, can you read this slide?
Okay, Aryan. Basic principles of quantum electrodynamics. QED describes how charged particles interact via the exchange of virtual photons. The theory employs Feynman diagrams to visualize interactions and calculate probabilities. It is highly accurate theory with predictions matching experimental results to many decimal places.
Okay, so Saksham, do you know about who is Feynman?
Yes, Aryan.
Do you know about Feynman? Uh, the person that we just mentioned.
Richard Feynman.
Yes.
Aryan, he was the American theoretical physicist. He is the best known for his work in the integral formulation of quantum mechanics, the theory of quantum electrodynamics.
Okay. So, you know that we have also done some presentations about his topics and about the double slit experiment and how it described that everything is going through every path at the same time, right? Okay.
Yes, Aryan.
So spontaneous emissions. So Saksham, can you read this slide?
Okay, Aryan. Spontaneous emission. Spontaneous emission is the process by which an excited atom emits a photon without external stimulation. It is a fundamental quantum process explained by QED. The rate of spontaneous emission depends on atomic properties and the surrounding electromagnetic field.
Okay, so so in this, what happens that an photon comes, and if it is at the right frequency, what would happen that it would make the electron go up an orbital, and then it will come down after some time. So this will release a photon of that exact frequency. So okay, Saksham, I have one question for you.
Yes, Aryan.
Okay, so how do objects get their color? Do you know?
Hmm.
Okay, so do you know?
Aryan, I think so. They get their color by these selectively absorbing some
Yeah.
wavelengths of light and reflecting others.
Okay, so do you know why are some objects transparent?
Mm, Aryan, I think so. The objects are transparent because light waves pass straight through them without being significantly absorbed, reflected, or scattered.
Okay, so you are right. So in transparent objects, what happens that the photons do not get absorbed because they are not the certain frequencies that the electrons required. So then they just pass through them. So Saksham, I have one more question for you. So when the photon gets absorbed, it is at a certain frequency, but when the photon uh, gets emitted, it is also at a certain frequency. So do you know what does that mean? Hello, Saksham. Saksham, are you here?
Aryan, can you repeat your question?
Okay. So when the photon is getting absorbed, it is at a certain frequency, and when the photon is getting emitted, it is at a certain frequency. So do you know what does this mean?
Aryan, I
Yes.
think so. When a photon is absorbed, an electron jumps to a higher energy level, and the photon's energy must exactly match with the energy difference between levels.
Okay. So uh, what does this signify? Do you know? Uh, okay. Do you have any guess? Okay. So the it means that the photon is getting reflected too. Okay. So when that photon is getting absorbed, it also has some momentum, and when it is emitted, it should uh, also have some momentum, right? So uh, do you know what does this mean? When the photon is getting absorbed, what happens to that extra momentum that the electron gets? Hello, Saksham. Hello, Saksham, are you here? Hello, Saksham, I can't hear you.
Yes, Aryan.
So, Saksham, I had a question. When the photon is getting absorbed by the electron, it also has momentum. So, what happens to the extra momentum? Do you know?
No, Aryan.
So, let's assume that we have an electron and there's a photon, and it gets absorbed and gets absorbed. So, the photon also had momentum. What would happen that the electron would feel a nudge from it, which would conserve the momentum. So when that electron is in the higher level orbital, uh, and then it wants to go at the lower level, so what makes the photon that is emitted? Do you know, Saksham? Hello, Saksham. Oh, Saksham, did you get my question?
I don't know, Aryan.
We have discussed it earlier. So my question is, when that electron is in the higher orbital, How does it go to the lower level by releasing that photon? Did you get my question?
Aryan, can you repeat your question?
Okay, so when that electron is in the higher orbital, and how does it release that photon and get down? Do you know?
Aryan, when an electron is in the higher energy orbital, it is in the excited state with excess energy to return to a lower, more stable orbital. It must release that exact amount of energy as a packet of light called a photon, which has a specific energy corresponding to the levels difference between the two levels, making them atom emit light and settle back down.
Okay, so how is that electron emitting that photon? My question was that. Hello, Saksham, did you get my question?
Aryan, what was your question?
So, like as you said, it will go down by releasing that photon. But what how is that photon getting emitted? Do you know?
Aryan, it might be an excited electron in an atom or a molecule drops to a lower energy level, releasing that specific amount of energy as a packet of light.
I think so. You didn't get my question, but how is that photon actually getting emitted? Do you know? Like, how does that electron makes the universe say that it is time, so I will get down and will release
Are
this
you
photon?
are you asking that how is that photon is getting emitted?
Yes.
Photons are getting emitted because when electrons lose energy, often by dropping from a higher energy level to a lower one in an atom, releasing that energy as a photon packet of light, or they are created from energy during particle antiparticle annihilation.
Okay, so I think you still didn't get my question. How is that photon actually getting emitted? Like how does that electron signifies that it is going to emit that photon?
I don't know, Aryan.
Okay, so the electron starts wobbling and then it gives a signal to the electromagnetic waves to release that photon, and then what happens that in between they are entangled to conserve this momentum and etc. So if the photon moves right, it would move a little left to conserve momentum, and after that they would be de-entangled and it will return to the lower levels. Okay, so quantum description of spontaneous emission. So, quantum electrodynamics models spontaneous emissions as a result of atoms coupling with the quantized electromagnetic field. The atom's field interaction causes the atom to emit a photon spontaneously. So, the rate of spontaneous emission can be derived using perturbation theory within the quantum electrodynamics framework. So, Saksham, do you know about the perturbation theory?
Yes, Aryan.
So, do you know about the perturbation theory in quantum electrodynamics?
Can you repeat because there is a lot of noise here?
Do you know about the perturbation theory in quantum electrodynamics?
Aryan, it is the perturbation theory is a fundamental to quantum electrodynamics using small corrections to a simpler solvable systems to approximate complex interactions, treating the electromagnetic coupling as a small expansion parameter.
So, what is in that theory? Do you know? Have you ever read about it?
Yes, Aryan?
Have you read about the perturbation theory? Like, what is in it?
No, Aryan, I made it a guess.
Okay. So, do you know about the equipartium theorem?
No, Aryan.
Okay. So we will discuss those theories in some other presentations. Okay. So the role of vacuum fluctuations. So vacuum fluctuations are temporary changes in energy that occur in empty space due to the quantum uncertainty. These fluctuations induce transitions in excited atoms, leading to a spontaneous emission. There are several essential aspects of the quantum vacuum in quantum electrodynamics. Breaking radiation concept. So, breaking radiation refers to the emission of photons during atomic transition, effectively breaking the energy gap. It is a spontaneous emission process constructing with stimulated emissions which require external radiation. Imagine you are running as fast as you can. You have a lot of energy because you are moving so fast. If you suddenly had to brake or turn a sharp corner, you would feel a big push. Electrons feel that same push when they zoom past a big atom. So, okay. Saksham, do you know what is momentum?
Yes, Aryan?
Saksham, do you know what is momentum? In the Saksham?
Aryan, momentum is a fundamental concept in physics representing the quantity of motion an object has calculated as the product of its mass and velocity, which
Okay,
is P
so
is equal to mu or no mv.
okay, so uh, the photons do not have any mass, but they still have momentum. Do you know why?
I think Aryan, due to their velocity.
Okay, so it would come as zero times their velocity. That will still equal to zero. Uh, it would still come as zero if we use the same momentum formula. Do
Okay,
you,
Aryan.
do you have any other guesses?
No, Aryan.
So in quantum electrodynamics and in the quantum world and in the more advanced physics, there is another formula of this momentum. So I do not have any. Just forgot about the formula, but I would remind you in the other presentation about this a more advanced concept of momentum. So uh, we can feel momentum when we go and we stop very fast. So there's a sudden push on us. So that also applies to the case of electrons, and when they're going near the nucleus, the positive charges are attracting it to the nucleus, but the electron is moving and it gets deviated from the path and it loses energy, and then that lost energy is emitted by making new photons to recover that lost energy that was lost. Breaking radiation. So, Sakshim, can you read this slide?
Okay, Aryan. Breaking radiation. As a fast moving charged particle passes close to the positively charged nucleus of an atom, the electrostatic force causes it to deviate from its path and lose kinetic energy because electrons can lose any fraction of their energy from a tiny amount of their kinetic energy in a single interaction. The resulting radiation forms a continuous spectrum of energies.
Okay, so has a fast moving charged particle, typically an electron, passes close to the positively charged nucleus of an atom. The electrostatic force causes it to deviate from its path and lose kinetic energy. Because electrons can lose any fraction of their energy from a tiny amount to their kinetic energy. In a single interaction, the resulting radiation forms the continuous spectrum of energy. So it depends how close the electron can get, and if it gets way too close and the electron gets captured, it would release all of its energy in a single high energy photon like an X-ray, and it will become an electron in that atom, and it will become a standing wave at that time. Breaking radiation and energy conservation. So the energy carried away by the photon balances the energy lost by the atom during transition. So quantum electrodynamics ensures energy conservation at the quantum level during spontaneous emissions. So this process involves a transition from potential to kinetic energy of the emitted photon. Why is it so special? Unlike quantum jumps, where light only comes in a specific color, breaking radiation can create any color or energy of the light depending on how much the electron slows down. This creates a rainbows of X-rays called a continuous spectrum. The faster it slows down, the stronger the light it creates. Quantum state evolution during emission. Before a photon is fully released, the atom enters a state where it is both excited and not excited at the same time. For a tiny second, the electron cloud wave function is a hybrid of the high energy shape and the low energy shape. During this mix, the electron cloud actually wobbles or vibrates at specific frequencies. This wobbling is what shakes the surrounding electromagnetic field to start forming that photon. So at the time they are entangled, if the photon moves to the right, it would feel a left nudge to conserve the momentum and everything, and then it will go down to the lower orbitals by emitting that photon. So thank you for joining us, everyone. So in this presentation, we talked about electromagnetism, quantum physics, spontaneous emissions. So thanks for joining and have a nice day.